These are your notes following determining the number and types of rational zeros for a polynomial function. It's going to follow the examples for Glencoe 7475. We're first going to take a look at example 1 using synthetic substitution. Synthetic substitution is actually the exact same as synthetic division. I'm going to put the x value that I'm evaluating in my little half box, and I'm going to pull down the coefficients of my terms. Notice, once again, I do not have a cubic term, so my coefficient becomes 0. And then I'm just going to go down in order from highest degree to lowest degree all the way to my constant here. All right, so we're going to pull down the 2. We're going to multiply. We're going to add. We're going to continue on with multiply, add, okay? So the only difference is when I start doing this and I end up in this position here of, well, clearly it did not produce a 0. What this value is just its y value. It's going to give me the coordinate, okay? So at 6, I have a y value of 2,453. It makes sense that It makes sense that synthetic substitution will produce a y coordinate because when it gives you just a 0, that is its y value because it's crossing the x-axis. So just as I mentioned before, synthetic substitution is pretty convenient because it's actually going to help us factor here. So let's look at example 2, where we're going to show that x plus 3 is a factor of this polynomial. If the quantity x plus 3 is the factor, the conclusion that it's drawing is the fact that negative 3 is my solution. So negative 3 is what I'm going to plug into synthetic division here. All right, so my coefficients, my x cubed, he has a coefficient of 1. My x squared has a coefficient of 6. Then we have a negative 1 and a negative 30 here. Okay. We're going to pull down the 1. We're going to multiply. We're going to add. We're going to multiply and add. And then finally, ta-da, we got a 0. So we have verified now that x plus 3 is indeed a factor because synthetic division has proven the fact that his y-coordinate is 0. And we know that it means he's an x-intercept. So x plus 3 is the factor, and what our quotient just produced is the other part of our polynomial, where 1 is going to be the coefficient for now our quadratic term. And now we're going to go down, and this just produced a trinomial, and so now we can continue to factor him down further. So here's our x plus 3, and this is going to produce the two binomials where we have an x and an x because our a is 1. So now I ask us the question, what multiplies to be negative 10 and adds to be positive 3? Well, the answer is going to be a positive 5 and a negative 3. And now here is the complete factorization of this polynomial. All right, last example for 7-4. I'm hoping you're recognizing the fact that we actually haven't identified what the zeros are. Hopefully you remember that you can take your factors and set them equal to 0 to figure out what the actual solution is. And please remember that these are rational roots that we're looking for. So if we produce something that's like the square root of something or an imaginary number, those are not imaginary roots. All right, so in this next example, we have a real-world problem where we're given the volume of a figure as well as one of the sides, and we're asked to figure out what the other sides are. Hopefully you remember that the volume is found by multiplying the length, oops, there's an L, times the width times the height. So they're all going to be multiplied, aka they're all factors. So the factor that I've for sure seen is the one side length of x minus 4, telling me the solution is going to be 4. So I'm going to plug 4 into synthetic division, and my coefficients for the total volume are 1, 3, negative 36, and positive 32. So I'm going to pull down the 1, multiply, oops, then add. 7 times 4 is 28. And then we have 28 plus negative 36 is negative 8. 4 times negative 8 is negative 32. And ta-da, we have verified that it is indeed a factor, but we knew that because it was a given side. So here's one of our factors, x minus 4. Now we're going to take our new coefficients, and we just factored out an x, dropping him down to an x squared now. That's where the coefficient of 1 came into play. And we have a plus 7x, and then a minus 8. So now it's turned into just a traditional trinomial here. So we're going to create our two factors here because our a is 1, so x times x. So then I ask you, what multiplies to be negative 8 but adds to be positive 7? Well, that's going to be a positive 8 and a negative 1. So here are our factors. So once again, in this really specific learning target, all you need to do is take your factors, set them equal to 0, and solve, and identify which of the roots are actually rational numbers. All right, looking at example 1 now, 7-5, where we're determining the number and types of roots produced while solving equations. First one's just a typical linear equation, so again, as I like to say, a throwback. So we're just going to subtract 3 from both sides, getting us x equals negative 3. Now the part where we're going a step further is declaring its nature, essentially. So we have one real root. You can even go as far to say as one real rational root, because negative 3 is a rational number as well as a real number. Okay? Looking at B, we're asked to, again, find the roots. One of the most basic ways to solve these equations is by factoring. So because our A is 1, I'm going to give it a shot to factor it. So then what multiplies be 16 and adds be negative 8, that's going to be a negative 4 and another negative 4. Okay? So it's important to recognize that this just produced the same factor twice. Okay? So what this essentially means is it's going to be a root twice. So if I set it equal to 0, we're going to have x equals 4. It's going to be one distinct root, but he's going to have two real roots. Okay? So two real roots. But I'm going to say, and go a step further and say one distinct root. Okay? Well, let's continue with our path of factoring to solve equations and see. I'm noticing both of them have an x in common. So I factor out an x, leaving me with x squared plus 2. And when I set both of my factors equal to 0 by the zero product property, I get x equals 0. And then I go to solve him. And I'm going to have to subtract 2 from both sides, getting me x squared equals negative 2. And when I take the square root of both sides, it's important to recognize that that quantity could be positive or negative. And I'm taking the square root of a negative number, giving me an I radical 2. Okay? So when we're looking at what types of roots were produced here, we were given one real root, which is 0. We were given 2 imaginary. Okay? Notice that the imaginary roots came in a pair of conjugates. Alright, the last one, x to the 4th minus 1. We can continue using our strategies of factoring. This is once again going to be a type of difference of squares. And when we set our factors equal to 0, x squared plus 1 equals 0, and x squared minus 1 equals 0. Over here we're going to subtract 1, getting us, again, we're going to take the square root of both sides. And we're going to get plus or minus. Well, the square root of negative 1, that's just going to be I. Over here, we're going to add 1, and then take the square root of both sides. And when we take the square root, plus or minus goes in front. The square root of 1 is just 1. So here are my 4 specific roots. Notice we have 2 complex, and we have 2 real. And those real roots that we have positive and negative 1, they are both rational numbers. Alright, now looking at example 2, where we're stating the possible number of positive real zeros, negative real zeros, and imaginary zeros, I'm basically being asked to use Descartes' rule of sign. Whenever I'm looking for possibilities of numbers of zeros, this is Descartes' rule of signs. So to determine these, I like to use a chart, okay? So I'm going to use my positive, my negative, and then my imaginary chart. Because the total number of zeros that I should produce here are 5 because it's a 5th degree polynomial. So we're starting here at x to the 5th, and he is a positive positive coefficient. And we go from a positive to a negative, okay? This is a sign change. When we go from a negative to a negative, this is not. Now once again, we go from a negative to a positive. He is also a sign change. And then we go from a positive to a negative, another sign change, and then a negative to a positive, again, a sign change. So there are 4 possible positive real zeros. But Descartes' rule of sign has a little bit of an extra bit to it. We can't just say 4. We're going to take this number and subtract by an even number, or in this case 2, getting me another possibility of 2. We're going to continue to do this until we produce an illogical answer. So if I'm going to stop at 0. Because if I take 0 and subtract 2, we end up with a negative quantity, which you can't have. The reason he added this rule or part to his rule was because if we had simply just said 4 and that was the only possibility, it would have to be true. Now to determine the negative number of roots, we're now going to need to plug in negative x in for x and see how it impacts the sign. So now we plug negative x in here. We're going to plug them in everywhere. Okay. One of the great patterns with this is the fact that if you're plugging it into an odd degree term, the sign will change. Think about it. A negative times a negative is a positive, so it's not going to impact what it's being plugged into here. Okay? So negative x to the fifth becomes negative x to the fifth. Because now our next term here is being raised to the fourth, it does not change anything. He is to the third power, producing now a positive 3x to the third. This guy won't change because he's an even degree. And this guy becomes positive 8x. And our constant term had nothing to plug him into. So then once again, I'm looking for sign changes. Going from a negative to a negative is not a sign change. However, going from a negative to a positive is indeed a sign change. And then for the rest of this polynomial, notice we're just going from positives to positives to positives. That's why the only possibility for negative real zeros in this case is 1. Side note, if there had been more, if we had had another sign change, the rule of subtracting 2 would still apply. So now I kind of create a little bit of a flow chart here to fill in my imaginary roots. Please remember we must add up to 5. So one of the scenarios is I could have 4 positive reals with 1 negative real, leaving me with only 0 imaginary, because 4 plus 1 is already 5. Another scenario that I could have is the case where I have 2 positives, 1 negative, then I would have to have a total of 2 imaginary. One last scenario that I could have is the case of 0 positives with 1 negative, leaving me with 4 imaginaries. And this little chart right here is how I document all the possible cases for roots of this polynomial. In this third example of the Glendon textbook, it's actually a situation where using Descartes' rule of signs is going to prove to be helpful because it's going to help us hone in on which zero we could use synthetic substitution on to actually find specific roots. Okay, so looking at our polynomial sign changes, we go from a positive to a negative, and a negative to a positive, and a positive to a negative, giving me the options of either 3 or 1 positive real root. All right, for negative, anything with an odd degree is going to change its sign. So now we have negative x to the third. He's going to stay the same. Then we're going to have a negative 6x and a negative 4. Notice that there are no sign changes, which tells me that there are going to be no negative roots. This fact right here, I could either have 3 or I could have 1, tells me to go to your XY table. Look specifically at the positive roots. So one of the options is plugging the bunch in, but go to your graphing calculator. Think smarter, not harder. When you type this function into your graphing calculator and are looking at the positive roots, you'll notice that 2 is actually a root of this polynomial. So I'm going to plug it into synthetic substitution here, leaving me with 1, negative 4, 6, and negative 4 as my coefficients. Okay. So then we're going to pull down the 1, multiply by the 2. Oops, lost my pen there. We're going to add. We're going to multiply. We're going to add and then multiply, and then ta-da, we verified it, not only just using our graphing calculator. So if 2 is a root, that means our factor is going to be x minus 2. Now the new coefficients are going to produce a reduced polynomial. Was to the third degree, now it's going to be to the second degree, so our new leading coefficient is 1. Then we have a negative 2x and then a plus 2 here, okay? So then if you try to factor this guy here, it wouldn't have worked. So what you're going to need to use to actually find the zeros, yep, you guessed it, the quadratic formula. So I'm actually going to let you take the time to plug it in, check your work in the Glendon textbook to see and make sure you got it correct, okay? So now we're going to look at example number 4 where we're writing a polynomial function of the smallest degree given some of the zeros. Given the zeros of 3 and 2 minus I, we can make a few conclusions. If 3 is one of our roots, then we know for a fact that the factor is going to be x minus 3, because it's always going to be the opposite sign. With complex numbers, they always come in pairs of complex conjugates, so one of our factors is going to be x minus the quantity of 2 minus I, and the other one will be his complex conjugate, x minus his conjugate of 2 plus I. Okay? So now we're just going to need to do a little bit of multiplication here. We'll leave x minus 3 alone because we don't really need to worry about him right now. So that's going to give reduced to x minus 2 plus I, and this guy will reduce to x minus 2 minus I. Okay? I'm going to multiply our two polynomials here, getting me nx squared. This is going to get me a negative 2x, and this is going to get me a negative ix. Then I'm going to take my negative 2 and distribute him, so negative 2x. This is going to get me a positive 4, and this is going to get me a positive 2I. Now we're going to do the I and distribute him, giving me an ix, which, yes, I see is going to cancel out. That's great. Then we're going to have an I times a negative 2, so a negative 2I. And then an I times a negative I. It's going to be a negative I squared, which is going to be a negative 1, so a plus 1. So now, x minus 3 came down from before. We're going to combine like terms. Here's our x squared. Okay, the negative 2I and the positive 2I will cancel out. So notice, those actually went away, leaving me with just real numbers. So we have a negative 2x and a negative 2x, giving me a negative 4x. We're going to have a positive 4 and a positive 1, giving me a positive 5. So then lastly, we just need to distribute this x minus 3 times this x squared minus 4x plus 5. So we're going to keep multiplying. X times x squared, getting me x to the third. X times negative 4x, getting me negative 4x squared. X times positive 5, getting me 5x. And we keep going. Here's negative 3x squared. Here's going to be positive 12x. And then here is going to be a negative 15. Notice I kind of lined myself up to combine like terms, leaving me with x cubed, a negative 7x squared, a 17x, and a minus 15 as our polynomial.